Alright, gang, here we go. This is for Chem 1, Unit 13, Part 2. We're talking about reaction mechanisms. Alright, so in the last video we discussed how chemical reactions take place and how generally, in order for reactions to take place, what we need is a collision, and two molecules, right? Two molecules, whatever they may be, or our reactants, need to actually run into and hit each other, right? And we get a little mini explosion here, whatever. And so they hit each other, and in order for them, we needed two things for a reaction to occur. We needed this collision, but that collision needed to meet two things. Number one, it needed to have sufficient energy, okay? Enough energy to meet the requirement. And this requirement that it's going to meet is this activation energy. Okay, the second requirement had to have is being the correct orientation. We'll discuss that here in a minute. But that first one is it has to have enough energy. Okay, and this energy that it needs we define as the activation energy. And it's the minimum energy required for colliding particles to have in order to react with each other. So these particles need to have this certain minimum amount of energy when they hit each other in order to have a reaction take place. Essentially, this is the defining factor of how fast a reaction can take. Okay, the lower the activation energy, the easier it is for those molecules to hit each other and have enough energy, and then the faster your reaction will go. All right, every single different reaction has a different requirement for activation energy, and it's all just dependent upon how much energy it takes to break the old bonds is essentially what it boils down to. All right, and when these two molecules hit each other, you can imagine there's a brief moment in time where these molecules are all together. So if we like kind of drew it out to the side here, we'd have this little monstrosity thing that I drew, and these molecules, just for that brief instant of time, these molecules are here, okay, and they meet this thing, and then afterwards, right, as more time passes, we might have something like this, where maybe we should label these guys as like A and B and C, and then this was A and B and C, and then this would be A and B and C. And so like in this specific instance here, we've got this moment in time where we've got our old bond between A and B is halfway broken, and the new bond between C and B is halfway formed. All right, and then here we're at the product stage, so this is our reactants, and this is our product. Okay, products. All right, now here in the middle is this new thing that is at the height of the activation energy, and we call that the activated complex. All right, and this activated complex is this idea of this brief interlude, or this really brief moment in time molecule that exists right when your collision occurs. And so it lasts on average less than 10 to the minus 13 seconds, and it occurs right after an effective collision. It's a very, very unstable arrangement of atoms, and it's really because those bonds are halfway broken and halfway formed. Whenever we have a chemical reaction, we know it's a chemical reaction because there's bonds being broken or bonds being formed. And so this is a very unstable arrangement, okay? And whenever we're talking about stability in a chemical reaction, or really anything in science, we're always talking about the energy. All right, think about yourself at the height of a roller coaster. If you're sitting here at a roller coaster and you're sitting up here at the top, say this is you on the roller coaster. All right, you're up here. If you're up here on the roller coaster, you're at a very high potential energy, gravitational potential energy. There's a lot of chance for you to fall down. You have a high potential to fall. All right, and so you feel very unstable. Whereas when you were down here, right, at the peak, or at the trough here, you felt very stable. Okay, so here's you down here all happy because you're down here at the bottom. Okay, so anyway, so when when we're talking about stability of molecules, we're really talking about how much energy do they have, and how much energy do they have in regards to something they could easily transform into. All right. Another word for an activated complex is a transition state. All right. So if you hear me refer to a transition state, or somebody else, you read something about transition states in your textbook, that's what they're talking about. Okay. And so this is called the activation energy is the energy required to form the activated complex. Is essentially what it boils down to. All right, now this guy here is a very important diagram. This is called an energy diagram, okay? And in the y-axis we have energy, Okay, and in the x-axis we have reaction progress. So as we go left to right, we can see our reaction goes from reactants, here's our reactants, to our products. All right, so in this particular reaction, we've got carbon monoxide reacting with NO2 to form carbon dioxide and nitrogen monoxide. All right, so these are our general reaction. These are our reactants and then our products, right? And so you can see here that the reactants are at a higher energy because they're farther up on the y-axis than the products. So the reactants are at a higher energy than the products. So we've got carbon monoxide, nitrogen dioxide here. Okay, and notice here we've got the activation energy is this barrier right here, and this is the energy required to make our reaction occur. So you can imagine these two molecules hit each other, and if they don't hit each other hard enough, they'll have a little bit of energy, but maybe not enough. And if they don't have enough energy, they're not going to be able to make it over the hill. Think about trying, riding that roller coaster. If that roller coaster doesn't go up that hill fast enough, it's not going to make it over the hill. And so in order for this reaction to occur, it has to hit hard enough to meet this activation energy. Notice also that it has to hit in the correct orientation. Look, in order for this activated complex, here's what the activated complex looks like. It's a combination of both of these guys. This is that new bond that's being formed right here, and then this is the bond that's being broken, right? That guy's being broken, and this one's being formed right here. And so what's occurring here is we form this activated complex. Now imagine if instead of the oxygen hitting the carbon, what if the nitrogen hit the carbon instead? It'd be at the wrong orientation. That would look something like this. There's your NO2, here's your carbon monoxide. If these two hit, that's not the correct orientation. No reaction would occur. That's no good. All right. So anyway, so we have to hit it in the correct orientation with enough energy, meet that activation energy, and then once we're up here, so this is our activated complex, right? This is our activated complex. We'll abbreviate that as AC, okay? And then we fall back down and we form and then we form our products over here. And notice that so these are our products. They're at a lower energy level, so energy is released. And this value here is the amount of energy that was actually released. And if we had actual values here, we could just subtract to figure out what that energy released is. All right, so we call this guy an energy diagram, okay? So we just looked at one that looked like this one, looked at like B over here. And we had our reactants going to our products. Here's our delta H, remember, so our activation energy, this is what we just talked about, our activation energy is right here. We'll call this EA for activation energy, all right? And then up here was our activated complex, right, AC. Okay, and so this is what we established before. Now this guy here, this is the energy released during a reaction, and this is known as enthalpy. All right, so this is the enthalpy is another measurement of energy, but it's energy at constant pressure. And since chemists do their science in a laboratory where we have constant pressure, enthalpy is what we run with, okay, as chemists. Okay, so anyway, so this is enthalpy, all right, delta H, and this is really just how much energy is released, okay, the change of energy. So as we go from reactants to products, we get a total release of energy. And you know that a reaction that releases energy is exothermic, right? So this would be an exothermic energy diagram. All right, because energy overall is released. Now, what I want you to be able to know is if we lose energy, okay, this is an exothermic process, but specifically it's a negative enthalpy, okay, and that's because we're losing energy, so it's negative. Right? Now A is a little bit different. Notice A, we go from our reactants to our products, still the same, but now our products are at a higher energy level than the reactants are. So this is an endothermic process. Okay, so if we gain energy, this is endothermic, and we've already established this before, but what's new is that an endothermic process has a positive enthalpy change. Okay. Let's see if we can identify the other things. The activation energy, right? Here's our activated complex again. That makes sense. And our activation energy would be this guy right here. We'll label this as EA. Okay, so there's our activation energy. Notice our activation energy is still from the reactants to the activated complex. Activation energy has nothing to do with the products. All right. So activation energy, reactants to activated complex, and enthalpy change is from reactants to products. Okay. So why is this important? Now, you probably have charcoal at your house. You use them for grilling or something else, and charcoal burns in oxygen pretty easily. However, you're not worried. I have charcoal in my garage right now. I'm not worried about my charcoal catching on fire and combusting and blowing up my house. And that's because the activation energy between that carbon and oxygen for that combustion reaction is really, really high. Okay, and it's so high that the oxygen will never hit hard enough to cause that reaction to occur. So it cannot occur at room temperature. All right, so it doesn't matter how many collisions of oxygen there are against the carbon, there's never going to be enough to break that OO double bond in the O2 and the CC bond in the charcoal. Thus, the reaction rate is equal to 0. So in order to get your charcoal to burn, you have to give it some energy, usually, just a little lighter fluid and a match, right? Okay, now this part here I think is the hardest part in the whole unit, and it's this idea of reaction mechanisms. All right, we're going to dispel a little bit of a sneezing tree here. Okay, so far in your chemistry world, right, we've looked at a reaction like this and we've said, okay, we have our reactants over here and our products over here. We go from our reactants to our products, and we've done a lot with being able to predict why this might occur. Now, with kinetics specifically, we're looking at, well, what exactly is concurring in order to make the reactants into the products. And so really, before we looked at this reaction arrow and we said, all right, well, this is just this mystery black box that we go from reactants to products and magic happens. We're going to take a little peek under the hood of what might be occurring between those. All right, so here we've got a reaction of chlorine reacting with methane. Okay, let me get rid of some of this stuff because now it's gotten kind of egregious here. We'll get rid of these. All right, so we've got chlorine reacting with methane, and it forms this methyl chloride and hydrochloric acid. All right, and I might have, in the past, you would have assumed, well, the chlorine and the methane, blah, 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 and they make these things. All right, and you might assume they all occur in one step. That's not really true. What actually happens is it goes through a set of discrete interactions called elementary steps. All right, and so these individual steps it goes through here are called elementary steps. Now, and they always have to occur in a specific order. So the first elementary step in this particular reaction is that chlorine needs to turn into and split up into two separate chlorine radicals. All right, so you got these two radicals, and you don't know what those are, but they split up into chlorines. And so now these chlorines individually can react with the methane, and then the methane forms the methyl chloride, and then one hydrogen all by itself right here, and then that hydrogen can react with this chlorine, leftover chlorine from here. So this chlorine here ended up here, we're reacting with the methane, and this chlorine ended up here reacting with the hydrogen, forming hydrochloric acid. All right, all these steps combined is called the reaction mechanism. And if we take these guys and we kind of pretend they're algebra and add them together, we can start canceling things out. All right, so here we've got a chlorine, Cl2. There's nothing to cancel on the product side of the chlorine here. The chlorine, this single chlorine could cancel with that chlorine, and then there's nothing with the methane to cancel, and then the hydrogen, well, that hydrogen could cancel with that hydrogen, this chlorine could cancel with this chlorine. So I'm canceling out things that occur on the reactants and product sides at the same time. And if we add these up and keep track of what was on the reactant side, we got a Cl2 and a methane reacting to form the CH3Cl and HCl. Okay, you can see that this reaction here is the same reaction we started with. So this is, indicative of the fact that this is a valid rate reaction or reaction mechanism. Okay, so this is called a reaction mechanism. Is all these steps all combined. So individually they're elementary steps, all of them together a reaction mechanism. The slowest step whenever you see a reaction mechanism, you'll always see them labeled as with speeds. Okay, the most important part of this is this step here. We're always looking for, well, which step here is going to be the slowest step. All right, and this slowest step is called the rate determining step. Okay, the rate determining step, and it's the one that you called it that determines the rate. Okay, it's the one that really determines how fast we can go, and it usually has the highest activation energy. Okay, and so we can and so the slow step is our rate determining step. It's the one that determines how fast we can go. All right, last little thing you need to know about reaction mechanism is this idea of intermediates. Okay, intermediates are molecules or radicals or ions or atoms that form in one elementary step and then get used up in another elementary step. So essentially everything that we canceled here, these are our intermediates. So our intermediates for the reaction that we just looked at here is this chlorine and the hydrogen. All right, all of this, since those are the things we canceled, those are our intermediates. All right. So let's look at this guy. It says, what is the overall reaction for this mechanism? All right, so we're going to look at this and cancel what we can cancel. So we got an NO2 here and then an NO2 on the product side, so we can cancel one of those, but not both of them, right? So we still got an NO2 there. Let's see, we got an NO3 and an NO3, so that could cancel with an NO3. All right. Cool. And that's it, right? So we got, so our reaction here would be NO2 plus carbon monoxide goes to NO plus CO2, right? This reaction we've looked at several times. So what would be our intermediates for this? Well, our intermediate, our only intermediate, remember, you would be tempted to say NO2 because it got crossed out. But really that NO2 was not formed in an elementary step. It was just an additional NO2 that we started with. The NO3 is our only intermediate. Okay. So this NO3 is the intermediate. Okay. Now the NO2 is another interesting thing. The NO2 is a catalyst. Okay, and you probably heard the term, we've talked about catalysts, I think, before in this class, and so, or you've learned them hopefully in biology or something. A catalyst is something that increases your reaction rate without getting used up. All right, so this NO2 was started with, okay, it helped start our reaction, and then we got it out again on the other side, so it did not get used up. So we got the NO2 and then the NO2. All right, so the NO2 is a catalyst, and the NO3 was an intermediate. Okay, so if we were going to look at that reaction we just talked about here, our reactants would be the NO2 and CO. NO2 and CO. All right, the transition state, so our first reaction would be this first reaction step here, going from this. So the transition state would be this NO2 bonded to NO2 would be the transition state. And the intermediates that we formed, would be these guys here, right? Because I keep going the wrong freaking way. NO3, NO3, right? There's our intermediate. And then it comes up here and we get our new transition state where NO3 reacts with our CO, right? So NO3 reacts with our CO. And then for our products, we get our NO and CO2. CO2. So this is an energy diagram that's slightly more complicated because it takes into account our individual steps. So we've got one elementary step occurring here and another elementary step occurring here. All right. We could also use this to give us an idea of which one would be the slow step, because remember the slow step is always the step with the lowest activation energy, or the highest activation energy. So this would be the activation energy for step 1, and then this would be the activation energy for step 2. All right, and so in order to figure out both of it, it's kind of hard to tell which one's actually bigger, isn't it? Let me see if I can hold up like a piece of paper or something like that, see if I can get an idea of which one. I don't know, they're about the same. So that's not very helpful, but really if you were looking at an energy diagram like this, you'd be able to see that the one with the bigger hump is going to be the one that has the lower activation, or the one with the bigger hump would have the highest activation energy, and that would be probably be your slow step. You could run with that idea. All right, so anyway, so that's it for part 2. Hope you had lots of fun. I think this is the hardest stuff in the unit, so lots of new material or new vocabulary and new ways of thinking about things that we haven't really hit on before. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.